talk about what the color of the sky is on Mars. Before I can do that, I need to talk about the colors of light. If you ever looked at how light passes through a prism, that is a triangular or pyramid-shaped block of glass, you see that white light gets split up into all sorts of different colors. There are other ways you can do this. If you look at DVDs, you also see it there. And that's because light is made up of lots of different colors. It basically is made up of all the colors of the rainbow all merged together. If we look at this in reality, here we have a white light. That light is being passed through a slit. That just makes it a little easier to see what's going on. That slit of light hits the prism. This is this glass block. And when it comes out at this angle, it is being split up into all its different colors. So this is just a cartoon version of that. So I've got light coming through a hole in a piece of card. I've got it hitting a glass brick that's triangular. And as the light gets spread out into its different colors, we see it spread out like this. And you can see it starts with red at the top, all the way down to violet at the bottom, through all the colors of the rainbow. Now this is important because this is how light really behaves. And understanding how light interacts with materials lets us learn all sorts of different things. So let's look at that a little bit. So how does light interact with stuff? So here I've got a block of material. It might be glass, it might be wood, it might be metal, it might be concrete. Now I've got some light that's going to hit it. When it hits it, some of that light's going to bounce off. And this is actually how we see most things, is through reflected light. When you look at the wall, when you look at each other, what you're seeing is light is bouncing from a light in a lamp. It's bouncing off the wall and towards your eye, and so you're able to see the wall or your hand or some other people. You are seeing reflected light. How much light is reflected depends on what the stuff is made of, what it's painted, all sorts of things. If it's white, then that means that nearly all the colors that are hitting it are bouncing back off. If it's black, it means most of the colors are actually being absorbed by the wall or whatever it's hitting. But if you get different colors, then that is some of the light that's being reflected. So if you're seeing a green wall, that means the green light is being reflected and the other colors of light are not being reflected. Now, some of the light might pass into the material. If it's glass, you know that most of the light actually passes all the way through. If it's wood, metal, concrete, most of the light bounces off rather than going through. But you've got all sorts of different materials, and what happens as it passes through can also be important. Now, you might get a reflection of the other side, so that might be like a mirror, but also you think about a piece of glass, the reason you can tell how thick it is that the light also bounces off the other side of the piece of glass. And then if it's a piece of glass, some of the light gets all the way through. And so we can, when we see light, we might be seeing it because it's bouncing off something and we're seeing the reflected light, or it might be because we're seeing light go all the way through, like when we're looking through a window. But this is kind of a little simplified. This is what's happening when we're looking at just a simple slab. So like a plane of a piece of glass. But there are all sorts of other shapes of things that can affect how light is reflected or passes through. So here I've got a few examples of that. If we start up here in the top left, we've got a piece of glass that's got raindrops on it. And those raindrops are affecting the light that's hitting it. So instead of coming straight through the glass, the light is bouncing off, or it's passing through the raindrops, but it's getting messed up on its way through. And so that's where light is hitting the raindrop and being affected by it before it gets to our eyes. If we come over here to the top right, we've got fog. What's happening here is it's water droplets again, but instead of like rain where it falls down, it's very small water droplets, and so they stay up in the air. Now, depending on how small the water droplets are and how spread out they are, so how densely packed or how much space there is between the droplets, that will determine how dense the fog feels. So sometimes you have fog where you can't even see your hand in front of your face. Sometimes you have fog where you can see, 100 feet, 200 feet, and it really depends on the water droplets. But here what you can see is what's happening is you've got light that's hitting, say, this tree, and some of that light that hit the tree does not bounce towards you and hit you straight away. unlike it would without fog. With fog, what happens is some of the light that hits the tree is then bouncing off the water particles, so it never gets to you, and that's why it looks foggy. And so this is another way that light interacts with material. In this case, we're talking about particles. So particles means things like dust grains or ash or smoke or raindrops or water particles. If we go down here to the bottom left, now what we've got is, this is a sandstorm. This is in the desert, this is in Arizona. And here we've got, it's behaving just like it is with the fog. There are all these tiny little particles of sand, and when light hits it, it bounces off and it can go in any direction. You can see just down here, you can still see into it a little way, but you can't see in it very far. But it looks different than fog, and that's because the particles, they are dust grains, they are sand instead of being water. And so it looks different. And so by understanding how the light is bouncing off of different particles, we can work out what the stuff it's bouncing off is made of. And that's basically what I do for research. Now, you can see here that they do look different, but it's all kind of messed up. And what you're seeing is what we call, instead of just reflection, yes, the light is being reflected, it's bouncing off some of these particles, whether it's sand or water particles. But it's bouncing off in all different directions because of the shape of the particles. Think about it. The particles are more or less round, and so it's bouncing off in all directions. And so instead of calling it reflection, we call it scattering, because the light gets scattered in all directions. There are other ways that this can happen. Here I've got a couple of pictures of forest fires. So here what you can see is that, you know, the smoke that's coming up from the forest fires, that's also lots of little particles. In this case, it's mostly made of carbon. It's the ash that's left over from burning trees. And that's what the smoke is. And again, it's scattering the light, so you can't see into there. And so it's affecting what happens in the atmosphere. Volcanoes do a similar thing, but what volcanoes are throwing up is more like the sand, only it's a little bit different. It's more like a black sand that you get near a volcano rather than the nice white sand that you're used to seeing on beaches. Okay, so that brings me to a question. I've talked about how light can, pass through something or just bounce off it, and then if it's scattered, that means it's bouncing off in all directions. But actually, in our own atmosphere, we have this going on as well, and it's why the sky is blue. What's happening is we have scattering. Remember that the atmosphere, that is the sky, it's full of particles. It's made up of molecules, that the air is full of oxygen and nitrogen and other things. And so what's happening is that as light comes into the atmosphere, it hits the atoms and molecules in the air, and it's going to bounce off. But how much it bounces off depends on the color of the light. Remember I said that, let's say you're wearing a green sweater, that means that that sweater is going to reflect green light, but not the other colors of light. Well, now what's happening is the blue light is going to bounce off of the particles in the atmosphere and go in all directions. The red light is going to do that less. So blue light does it, actually violet light does it most, and then blue does it a bit less, and then green a bit less, and then yellow a bit less, and red is the least. What that means is that when you're looking up in the direction of the sun, don't look directly at the sun, what you're going to see is that the light that's coming down from the sun, some of it is being bounced off in all directions. And so it's going to bounce in all sorts of different directions. And it's going to bounce off another molecule, another molecule, another molecule. And that's why the sky looks blue. And then we have the red light that's not being bounced around so much. And so if you're looking in the direction of the sun, you also get redness towards the sun. So in the middle of the day, you tend to see the sun is actually slightly yellower than it would be if we didn't have an atmosphere. But if you're looking at it at sunset, you're actually looking through a much longer path through the atmosphere. And so the sun looks redder than it would otherwise. That's all to do with this scattering of light as it bounces off all the atoms in the atmosphere. Now, sunsets look red anyway, but if you have dust particles like the sand that we had in the sandstorms, or you have a volcano that throws up lots of stuff, or even pollution, pollution that comes from factories and things is also mostly dust. That throws up these particles, and that makes the atmosphere, all of the light in the atmosphere bounce around differently. And so we can get, with just a small amount of dust, even prettier sunsets, more reds than we would otherwise. So depending on what the size of the particles are, is it atoms and molecules, or is it dust grains, or is it water droplets, we get different ways that the light is bouncing off, and so we get different colors in the sky. So we can have the blue sky when it's just bouncing off atoms and molecules. We have red sunsets when it's bouncing off of dust, and then we can have white or even black from having water droplets, and that's when we have fog or clouds in the sky. Okay, so let's talk about the sky on Mars. So I just said that, you know, as light goes into the atmosphere for the Earth, it gets scattered around. The blue light gets scattered, but the red light doesn't, and so our sky looks blue. Now, Mars has a very thin atmosphere, so we might expect to see the same thing, right? We might expect to see that the sky would be blue on Mars for the same reason that it's blue on Earth. Well, let's take a look at what we have for images of the sky on Mars. So this is actually one of the first images of the sky on Mars. This is from the Viking lander. This is 1976. I would have been just starting elementary school at the time that this happened. And you can see the ground looks kind of brownish, and the sky is almost pinkish. It's kind of, it certainly doesn't look blue. But we really thought that the sky was going to be blue. So here you can see an image where you've got that kind of pinkish reddish color in the sky, and the ground is reddish. But we corrected it, assuming that actually the sky was going to be blue. We'll come back to this idea later. But it turns out that, you know, we might not know what color things are supposed to be. Sometimes when you take a photo, it doesn't get the colors right. And that's what we thought was happening here. Now remember, that was 1976 when we sent the first things. This is a much more recent image. And what you're seeing here is, these are all the same image taken from one of the rovers that's landed on Mars. And this is what the Jet Propulsion Lab that deals with all the rovers, this is what they got back as an image. And this could be exactly right, or it might not be. Now, one of the things we do is we try to calibrate. What that means is we try to basically adjust it to make it so it's the right color. So this middle image basically is taking something in the picture and saying, okay, we're pretty sure that, say, this shadow here is actually black. So instead of being grayish like it is here, let's make it black. And let's see how that adjusts the rest of the picture. And so you get an adjustment. And then this image here is saying, let's assume that something in the picture is white. Let's say there's something that's reflecting and it's white. Let's find the palest thing in the picture. Let's make that white and adjust it that way. And you can see that they all look slightly different in terms of the colors. And so getting exactly the right colors is tricky. And you probably won't remember, but when digital cameras were new, you would frequently get weird colors in the pictures because the cameras weren't that good at calibrating, at working out what color things were supposed to be. So that brings us to other things that have been sent up since. So remember, Viking was there nearly 50 years ago, 45 years ago. But we've sent a whole bunch of other probes since. This was Pathfinder. Pathfinder was this lander that it landed, and then it had this little rover here. So this is a picture that was taken of the rover from the lander, and the rover is called Sojourner. And by this time, we were doing a better job of finding ways to calibrate. That is, you have things that you know what the color is, and you can point the camera at that, and then use that to adjust and make sure you've got the colors right. And so now what we see is, oh, look, the sky is actually that kind of pinkish brownish color. It's not blue. Let's keep going. Here we have Opportunity. Opportunity actually functioned from 2004 to 2018. There were two rovers that were dropped in 2004. The other one was called Spirit. Spirit lasted until 2011. Opportunity lasted till 2018. They were actually both only supposed to last for 90 Mars days. That's about 92 Earth days. So about 3 months. And instead, Opportunity, sometimes called OPI, lasted for a full 14 years. Now, what you can see here is the greenish is kind of a weird haze that's coming off the ground. Here you can see the tracks of the rover. It's looking back on where it's come from. But again, you can see the sky as that kind of orangey, yellowy, browny color, but not blue. And this is another picture from Opportunity. So here you can see it's definitely kind of this dirty color. And then that brings me to Curiosity. Curiosity was landed in August 2012. It's still functioning, so we're still getting images. Here you can see, this is one of the many selfies. Curiosity really likes taking selfies of itself. And you can see here, this is a little bit fuzzy. I think there was a little bit of a sandstorm going on. And you can see the sky is again that kind of orangey, pinky, browny color. Here's another one. The sky's a little clearer. And now you can see it's still that same color, but you can see the rover a little more clearly. You can see the color of the dust that's landed on it since it was been there as well, is the same sort of pinkish, reddish color. Here's another one, and this is actually during a sandstorm, and you can see just how yellowish it's looking now that there's lots of sand. And if you remember what it looked like with that sandstorm over Arizona, you can understand how all the dust that's around is affecting what the colors look like. I like this picture, and it makes me think that Curiosity is trying to be WALL-E. So when we look at Mars sky, it's generally some sort of brownish, yellowish, pinkish color, often called butterscotch. But it really does appear to be this color. From all of the rovers that we've sent in the last 25 years, we're really seeing that the sky is not blue. During the day, what we see is this kind of yellowish, pinkish, brownish color. And so the sky on Mars is not blue, it's butterscotch. But let's look at sunset. And remember that sunset on Earth tends to be reddish, yellowish, orangish. And what you get here, so here these are pictures of the sunset. Here you can see how this was taken in different pieces and kind of stuck together. And you can see how the sky is kind of that pinkish color again, reddish pinkish color away from the sun. But if you're looking towards the sun, it's now blue. This is completely the opposite of what we see on Earth. At sunset, if you look away from the sun, you're still going to see blue sky. But if you look towards the sun, it's going to look reddish. And it turns out that all of this can be explained by two different things. One is that Mars's atmosphere is very thin. It's like you're being at really high altitude on Earth, above the mountains. And so the air is so thin that you don't get much of that scattering that makes the sky blue. At the same time, there's lots and lots of dust particles in the atmosphere, and it is those dust particles that are giving us this reddishness in all directions. At the same time, because of the specific type of dust particles, the same particles that make the surface of Mars reddish, they also reflect in a certain way, and so what we get is this bluishness at sunset. And so I'm going to end there and just remind you that the sky on Mars is butterscotch during the day, and the sunsets are blue, not red.